Today, before we get going on the material, I'm just going to share an econometric research study that answered one of the questions you guys brought up at the very beginning. So this is kind of a cool study. Let me just make sure I know what page that we're on right now. So this study is called Double or Nothing. And what they do is they double the salaries that teachers earn in Indonesia, and they do it randomly. So what they do is they take 300 different schools and they randomly assign half of those schools to double the salaries of teachers. And what they're interested in is to see if doubling the salaries of teachers affects their productivity, how much students learn. Oh, I didn't share my screen, I'm sorry. How much students learn. So do teachers work harder when they're paid more? This is a great question. So why do we think that teachers might work harder when they're paid more? So sometimes we find that, like, when you do something nice for someone, they do something nice for you. So we call this gift exchange or reciprocity. And we also sometimes have an efficiency model of wages, which is like people work harder so that they don't lose their job when we pay them more. So when we pay them, so Costco, for instance, they're an example of efficiency wages. They pay higher than typical wages so that they can attract better people, and that the people they hired really want to keep their jobs. So they hustle more at work. So this is a nice test of that theory, where they just doubled what teachers were paid. And I do a lot of work on public school teachers, so this is kind of an interesting paper for me in other ways as well. So this is the main table. The nice thing about experiments is that they're super simple econometrically. So basically you have a treatment and a control group, and you're just going to compare those two groups and see if the students are learning more in one group or the other. So this row right here, I don't know, I'm having a hard time controlling this, but all of these numbers, 0.00 under math is how much different students in the treatment schools perform in math than in the control school. So you can see it's just 0. In science, they do about the same. In Indonesian, they do about the same. English, etc. So this is the year. This is the year after they're treated, and this is the second panel down here is the year 2 years after they're treated. So there's just no changes in the achievement of the kids that are bigger than the standard error. So that just means that this one's statistically significant in science, but usually you get a few statistically significant things even if there's no effect. So the fact that we have, 30 coefficients and only one is significant at the 5% level, or the 10% level, means that there's really no effect here. So it's just kind of an interesting test, because a lot of people would say, oh, if you just paid them more, you'd get better teachers, or the teachers would work harder. But that doesn't appear to be the case from experimental evidence. Okay. Questions on that, or questions from yesterday? Okay. So today we're going to finish our lecture on regression. Oh, and just a little bit of housekeeping. Okay, so your homework is due, that we did on Monday. No, that we did on Tuesday is due today at midnight. The homework that we did together yesterday is due tomorrow. And, we did all of that. If you weren't here for that, all of the work that we did together is on the video lecture. So that if you weren't here for some reason, that's totally fine, and you can look at the lectures. But hopefully all that is already done. You've already completed all that. It's just crazy to have a semester that's compressed into 6 weeks. It means that we have to be really quick. So what that means is that next week sometime between Friday and the following week's Monday, we need to have our midterm exam. So I'm trying to just kind of get you guys ready for that and fit the material in at a pace that is kind of gentle and helps it make sense. But one thing that I did is there will be a short quiz, just 5 questions on this Friday. Or if you want, you can take it Saturday. I'm going to make the deadline Saturday, but I kind of plan on you guys taking it by Friday. I actually wrote what each question was about in the email I sent you yesterday. So it was like, what's econometrics? What's a normal distribution or a uniform distribution? What is an error term? What does ceteris paribus mean? And interpret a simple regression. So there are 5 questions. Those are the 5 questions. And so it should be really simple. It's open book, open note. And you've got it's 5 questions and the quiz is 15 minutes. So you've got tons and tons of time to do well on that. But I just wanted to give you some quizzes so that you knew what the test might look like. And then next week we'll have another 5-question quiz, probably on Wednesday. Just trying to give you lots of opportunities to get points and a couple opportunities to see what questions look like on the test. And then we just have to decide whether the test should be next Friday, that is a week from tomorrow, or whether you want it over the weekend on Saturday, or whether you want it that Monday in place of class. I'm just trying to give you, I think I will try to give you the topics for each quiz, in part because I think that you can go back and study it. I think like it probably helps you to learn it if you know what might be on the quiz before. So this is like, I didn't give you the exact wording of every question, but I think it's helpful. I'm going to try to give you, they're not written responses, they're multiple choice. And I might not always give you all 5 topics, but I'm going to try to give you kind of a heads up of what kind of topics are on each quiz. So the question is, and we'll play it a little bit by ear, but would you guys prefer to have the exam next Friday, next Saturday, or the following Monday? Can you guys just put it in chat which you'd prefer? And we might have to adjust it a little bit, but we'll see. Okay. So we can try to do Monday. Monday gives us the most time to get through all the material that's on the midterm, and probably gives us a day to do a little review session. So that'd be good too. So my goal is we'll get through lesson 4 and part of 5 today. And then next week we need to get through lesson, I think it's 6 and 8. And then we'll have a review day. So I think that all fits in the 4 days that we have next week before the weekend. And yeah, and the exam is not hard. It's intended to be super straightforward. And I'll give you a list of topics that's on it, kind of not sample questions exactly, but I'll say, you'll need to be able to interpret a regression. You'll need to be able to tell me what you need to know something is causal. And the key for causal is you need the groups that are treated differently. So say people with high education, low education, they're different they're the same in other respects. That's ceteris paribus. But yeah, I'll give you a big list of kind of the topics that are on it, and it should not be complicated. I think that the test will probably be 50 questions, and you'll have like an hour and a half. The reason that you don't have tons of time per question is I actually want you to study for the exam. I don't want you to, what I've learned is that if I say it's open exam and you have as much time as you want, There's just not a lot of learning that goes on. It's a lot of, people just wait for the test and then they take every question and try to go and find the answer. But that's just a really bad way of learning the material. You have to kind of see how it, take the time, go through the study guide and the lectures and just try to bring together the concepts that we've talked about. It's really, really hard to learn in an exam situation. Very difficult to learn. So that's why the test is timed, so that you don't really have time to go through and look up every answer, because I really want you to study. Okay, does that make any sense? Okay, sounds good. Cool. So today we're back on regression. Let's just do a little rewind. So regressions are pretty cool, pretty cool. So we're usually interested in some sort of equation like this, where we're interested in the relationship between some x variable and an outcome variable y. What's the relationship there? And to describe that relationship, to begin with, we're just going to have two parameters. These are called parameters. And we're going to choose these two parameters, beta naught and beta 1, to minimize the distance between the data points and the line that goes through them. So we'll pick a beta naught and a beta 1 that minimizes the distance between that line and the data points. We learned a couple of interesting things. One was that when we add up all of the error, all of the residuals, all these error terms, we have a lot of words for these residuals. That means it's the part that's left over that the model doesn't explain, residuals. We can call them error terms, or the error. When we add those all up, they equal 0, which is super interesting. And that just reflects the fact that we're putting the line in between all the data points. So when you add all the error terms up, they're going to cancel out. And then we also have this cool thing where if we calculate the covariance between x and the u, though the covariance between x and u is also 0, which also I'll show you soon that also just reflects that the line is going through the middle and it's not straying above the points or straying below the points at any part of the regression, at any part of the data. Okay. So that's basically how we're choosing beta naught and beta 1, is we're choosing the beta 1 that makes the error sum to 0, and we're choosing, the beta naught that makes the error sum to 0, and the beta 1 that makes the errors uncorrelated with the x. Let me just write that. So this is how we choose beta naught. Okay, and then this is a condition that helps us choose beta 1. Now we'll go over that again in two forms, I think. Okay, so we're doing this part that I'm not going to quiz you on or test you on heavily. This is just so you know that where we're getting these things. And basically we are trying to select the betas that minimize the sum of the squared errors. And we know that the error term can be re-expressed in terms of beta this way. So then all we do is we're going to take the derivative of this function here with respect to beta naught and beta 1. And that gives us two first order conditions. First order condition meaning we take the derivative and set it equal to 0 to find the minimum. What beta 1 and beta naught minimize the distance between the line and the data points. Okay, so we can use both of those to calculate beta, or to derive beta naught. So first we're going to derive beta naught, and then we'll derive beta 1. Beta 1 is it takes some really tricky algebra. So we'll glide over it a little bit simply because I'm not going to test you on it. But just so you know, this is where things are coming from. So first, we start with this first order condition here. Initially, we had that it had a 2 here. So all we're going to do is multiply both sides by 1/2. So all that's going to cancel out. It's just a constant, so it doesn't matter too much. And then we're going to do a fun trick, and we're going to multiply both sides by 1/n. Just remember that 1/n times 0 is still 0. And then we're going to use some of those, what are they called? Some of those formulas that we learned, I think, in the last lecture deck, where this, we can break this sum into 1/n sum of yi plus 1/n times the sum of beta naught plus the sum of 1n times the sum of beta 1 xi. Okay, so what is this? This first term is just the average of y. Okay, and that's just a simple thing. That's just, we're summing up all the y's and dividing by n, and that's just the same as the average. Remember that when we sum beta naught n times, it's equal to n beta naught, because beta naught is a constant. And then we're just going to divide it by n. So that is, that's where this comes from here. Okay. I'm sorry, this isn't a plus, this is a minus. Oh boy. Okay. And then this last term right here, we can take the beta. Can we take the beta out? We can take the beta out. Wait. But this is going to equal 1/n times n beta 1 x bar. Okay, and the n's cancel out. So this term is where we get this bit. And this again is a negative, not plus. Okay, so now we're in a good place because this is just simple algebra. And we can rearrange the terms so that beta naught is on one side and the rest of the terms are on the other side. So we know that beta naught is equal to the average of y minus beta 1 times the average of x. So there is a kind of a deeper interpretation of that, but we don't need to worry about that right now. So that basically all we've done is we've taken the first order condition for beta naught and we've used it to calculate how we find beta naught. Okay, take the first order condition, we find the beta naught that minimizes the distance between the points and the line. Okay, let me take a break. Questions here? Cuestiones. Yesenia, Warren, Stephanie, Saul, Noah, Ned, Manuel. Derek and Devin, thanks for having your cameras on. I appreciate it. Noah, thanks. No question, no questions. Okay. Cool. Okay. So then the second one is we can do most of the work, but there's a step that's quite difficult. So first, this is the second first order condition right here. So this is when we took the derivative of that minimization piece with respect to beta 1. So what is the beta 1 that we need to minimize the distance between the line and the data points? And we set it equal to 0 because that's where the minimum is. And then all we do here is we know we have a formula for beta naught. And that formula for beta naught is y bar minus beta 1 times x bar. Just that's the thing that we found just in the last slide. These are equivalent. Okay. And why do we do that? Well, we want everything to be in terms of beta 1. It's just messy. We need everything. We need this whole formula to be in terms of beta 1. We don't want any other unknowns in this formula. Okay. So then we're going to combine terms. So I'm going to rearrange this. So that's where that term comes from. And then beta 1 is on these two terms, so we can factorize it out and just have x bar minus xi. And then remember, we can split up a summation. This is just taking the same summation and breaking it into pieces. Sometimes it's going to make it a lot easier because this is going to allow us to take this beta 1 and put it on its own side of the equation. So watch this. It allows us to, we're going to subtract this part and bring it over and then divide both sides by this part. And that's going to allow us to isolate beta 1 onto one side of the equation. So that's where we get this. Okay. So that's where we get this. And then this is just different sort of ways of expressing the same thing. So we're just multiplying through all of the x's and gathering terms. And we get to this, which is, if you kind of look at it closely, this is just on the top, this is just the covariance between x and y divided by the variance of x. And this should look familiar. So that means that the beta 1 is equal to the covariance of x and y divided by the variance of x. So that's nice. That's just exactly what we've found. So now, if you wanted to, you could show to somebody why beta 1 is equal to the covariance between x and y divided by the variance of x. And you could show somebody why beta naught is y bar minus beta 1 times x bar. So it's kind of cool. You could show that if you had a skeptical mathy friend, you could explain why we choose beta 1 and beta naught that way. This is just some more algebra for this step right here. This is a tricky step. This will just show you where that step comes from, but you don't need to know it. Okay, let me stop there. Questions here? Cameron, Denelson, Derek, Devin, Esmeralda. Ibrahim, do you go by Ibra? Okay. So we're just going to review what we did in short. So if we have two unknowns, beta naught and beta 1, in our regression equation, it looks like this. We're going to set up a minimization problem for the sum of squared errors. We're going to take two derivatives. That's what a first order condition is, a derivative of the sum of squared errors. with respect to beta naught, and then a different one with respect to beta 1. Okay. So then we get two equations. Those two first order conditions are each an equation, and that allows us to solve first for beta 1, for beta naught, and then we can plug beta naught into beta 1 and solve for the second, solve for the other beta 1. Okay. Let's see. Okay, so there's another way that people, that econometricians think about this, and they're slightly different. The textbook, for instance, is going to use two assumptions. The first assumption is that the expected value of U, of the residuals, is 0. And the second assumption is that the covariance between X and the residual is 0. So notice that these are actually the same, or at least very similar, to our two first order conditions. So notice that this is the same as UI, and this is the same as UI. And so these are this one is exactly the same. This is exactly the same as this assumption. And this is very similar to this one. We're going to have something like the covariance between X and U is required to be 0. Okay. I don't know what that. Okay. So so now we're past kind of the bummer part, which is the math and the derivation. This is kind of the fun part. What do we get to do with the regressions? What do we learn with our results? So the first is, we're interested in the relationship between education and wages, and we are able to estimate some sort of relationship based on the data that we have, what wages are and what education are for each person. And that gives us an intercept and a slope parameter. And so the main question is, how do we interpret our beta 1 as a derivative? So the takeaway is that beta 1 is essentially the derivative of the predicted value of wages with respect to education. So all that is how do wages change on average for a change in education. And when we say change in education, we mean if you increased education by 1 unit from 5 to 6 or from 12 to 13, how much do we expect wages to change? So the beta 1 is just the derivative of predicted wages with respect to education in this example. Okay. So I might say, I might have a data set for you. And I'm so sorry, I don't know why I'm tired. I went to bed at a great hour. And I say, this person is earning $10 an hour and her education is 10. How much more would she earn if she got an additional year, is she predicted to earn if she had an additional year of education? And if you just looked at the regression and you found, oh, look, beta 1 is the slope of wages with respect to education, and she's increasing her education by 1 unit. So all we need to do is multiply 1 by beta 1, and that would give us her predicted change in wages for a 1-year increase in education. So what if instead I said, her education, she's going to go to school and get an associate's for 2 years. What is the predicted change in her wages? How would you calculate that? So this question is definitely worth thinking through. It would be good to have it and kind of thought through. So the derivative is how something changes with a 1 unit change in our X variable, education. So if her education was increasing by 2 instead of by 1, we would multiply the derivative by 2. So say our beta 1 was, your wage goes up by a dollar for every year of education you have. We would say, well, her education is going up by 2 units. So her expected wage will go up by 4 units. By 2 units. Beta 1 equals 1 times the increase in education is 2. So that would be 1 times 2 is 2. There are other ways to do it. You could calculate her wage with 12 years of education and with 10, and then just subtract them. And that will give you the same answer. So hopefully one of those, I think we'll have some examples like that we'll do together. Okay. So this is our data, or are these points. We are going to fit a line. This red line fits through the middle of the points. And the beta naught is the y-intercept, and the beta 1 is the slope. How does y change for a unit change in x? So it doesn't actually matter how large you draw this triangle, because you're dividing the rise by the run that you used to get the rise. You'll always be getting the y change for a 1 unit change in x, because you're dividing by the run. Okay. So if I gave you this, I won't do this, but if I gave you this slope and I gave you a ruler, and you could measure the height of any triangle on this line and the width of any triangle on this line, it actually doesn't matter what triangle you draw. You'll always find the same slope on a straight line. Okay, let's do some examples. So this is kind of fun. So that we have this fun regression where we're regressing CEO salaries on firm profits. So as a firm makes more money, how much do they pay their CEO? What is the predicted CEO salary if a firm makes $800,000 in profits? So the way that we're going to do this is it's super simple. It's like 7th grade math or 6th grade math. We're just going to plug in 800,000 into the equation. So we're going to get CEO salary is equal to 300,000 plus 0.15 times 800,000. So I need to do that. 1% of 800,000 is 8,000. 8,000, I think, times 15. That should be easier the other way. So 40 was 8 times 15, 40. So something like has anyone had a chance to do this yet? Do the math with a calculator real quick.
Yeah, I got the same number as you, Professor.
Oh, perfect. Awesome. Perfect. So all we did is we plugged in 800,000 into the equation, and we get something like $420,000 is the predicted salary of a CEO making whose firm is making 800K in profit. So that's pretty. I would like to make 400K. That'd be fun. Okay, we could redo the deck or something, or go out to dinner. How much does a CEO's salary change if the firm's profit decreases from $800 to $500,000? Okay, so this is actually a little bit of what we were talking about in the previous slide. There are two ways to do this. I wish I had a better pen, because the easier way, whenever I say what's the effect of a change, let's see here. What's the effect of a change would be, okay, what's the change in X? And the change in X is 800,000 minus 500,000. And that's 300,000. And then you're gonna use this change in X and multiply it by your beta, which is 0.15. So 0.15 times 300,000, it's 3,015. So it's like 40. 1, 2, 3, 45. What do you think here? Is that wrong? Is it 45,000?
Yeah, I got 45,000 too.
So that's one way to do it, is you just take the change in the X. A way to do that, that's maybe, it can just kind of be easier in your mind, but it takes more work to do, is to do the following. We could take the CEO's salary where the profit is 800K, and subtract the salary that we would calculate when the profit is 500K. Okay. And the reason that that is the same is that you're basically going to calculate beta naught plus beta 1 times profit. I'm just going to make it simpler. When profit is 800, okay, minus beta naught plus beta 1 times 500, okay, and then watch this. Is that as we look at these two, all we're going to have, sorry, I have to go into this space below, but it's going to be beta naught minus beta naught plus beta 1 times 800K times 500 minus 500K, sorry, 500K. So these are going to cancel out, and all you're going to be left with is exactly what we already had, which is 45,000. Okay, does that make sense? So what you can either do two things. You can just take the difference in Vx and multiply it by beta, or you can calculate what the total salary would be for if the profit were 800,000 minus the total salary that it would be if the profit were 500,000, and then just subtract those two, and you'll get the exact same answer, because you're doing the same thing. You're canceling out these beta naughts, and therefore it's the same math. You don't have to think about the derivative if you do it this way. Does that make sense? Let's see, how are things going? Let me check in. Esmeralda, Ibrahim, Kimberly, Katrina, Levi, Manuel, Neb. Makes sense. Okay, cool. That's going okay. All good. Makes sense. You guys are just with it. I don't know what happened to you. I don't know what water you're drinking, but it's working. Okay. So that's good. What would the firm's profits need to be in order for the CEO to earn $0? See, this is always fun. So what we're going to do is use this formula that we have up there, and I'm just going to put it. I'm going to put it up here so that we can do have a little more room in case we need it. But we're going to say what does firm profit need to be for salary to be 0? So we're going to put 0 in for the left-hand side, 300,000 plus, why it's giving me such a hard time, 0.15 times X. And then we're just going to solve for X. I don't like this right here. Just put a little dot. Okay. So then we're going to do, we're going to say, we're going to take 300,000 over to the other side, subtract both sides by 300,000 equals 0.15x, and then x needs to be negative 300,000 divided by 0.15. Does anyone have that handy? Does anyone have a calculator? Let me see. Like 2 million. Yep, perfect. Ooh, you guys, 2 mil. So if the company is losing $2 million, that's when you predict, good job, Ibrahim, thanks. And Yesenia, you guys are on a roll. If the company is losing $2 million per year, you would predict, that's the only time you predict the CEO salary to earn $0. But if he or she is earning $0, you probably think they would just quit. They probably wouldn't be there for very long. Okay. Questions on that? Questions on all that? So those are very typical of the kind of question that might be on a quiz or a test or something like that. Okay. What's the predicted employment rate? Okay, so here we have another, this is a very big, obviously, big question for economists. How does employment affected by minimum wages? We're always worried that if you're forcing people to earn more than they're naturally worth to a company, to a firm, to an employer, then the employer is going to be less likely to hire that person. So we have this model where we're going to predict the employment rate, and the employment rate is 97% of people minus 0.02 times the minimum wage. So what's the predicted employment rate if the minimum wage is $7 per hour? Super fun, super simple. We're going to say 0.9, just plug it in to this formula. We're going to get it's 0.97 minus 0.4, which is going to be 0.83. Okay, so all we're doing is plugging 7 into this formula. That's all we're doing. If one state has a minimum wage of 6 and another has a minimum wage of 11 per hour, what is the predicted difference in their employment rates? So this one we can do the same way as we did before, but the simpler way is to say we've got a difference of change. The difference in x is equal to 5, and it's 0.02 times 5 is equal to 10. So we think that the predicted difference in their employment rates is 0.1, or 10 percentage points more employment in the place with the lower minimum wage. You can do the exact same thing by just plugging in 11 and 6 to that equation, and then subtracting the 2. Okay. So I feel like you guys are probably all on board with all of that. Any questions here? Stephanie, Warren, Kimberly, Katrina, Ibra, Esmeralda, Levi, Griff. Okay. Devin, Kimberly, no questions. You guys are just crushing it. Okay. No questions. Okay. So the last little piece of this slide deck is that we have a statistic to measure how well a line fits the data. Okay. And remember that this is the best line. So this isn't just any line fitting the data. This is how well does the best line we could possibly draw for the data points fit. This is more a question of how do the data fit rather than how does the line fit in some way. So here we've got, you can see that there's just tons of space between the data points and the line. So we'd say probably this line doesn't fit very well. It doesn't explain very much of what's going on in the data. By contrast, this line, you can see there's just it's tight. These are some data with skinny jeans. The line is just right on top of those data points. So this is a tightly fitting model. Okay. So we'd say the line fits very well, these data. So we have a couple measures of, we have two statistics that we use to calculate our fit measure. The first is called an SSR. I actually don't even remember. Let me look at this up really quick. Okay, it's the sum of squared residuals. Sum of squared residuals. So all we're doing here is we're subtracting each of the y's from the predicted value of y. So basically, if this value is big, it means that the data are actually quite far from the predicted values. If this value is small, it means that the data points and the predicted values are very close to one another, right? There's not a lot of distance between the data and the predicted value. Okay, then we also have a measure. Let me just see, what's SST? Okay, sum of squares total. So this is the sum, the total sum of squares rather. Total sum of squares. And this is just going to basically measure how much spread is there in the data to begin with. And the way that we kind of measure that is just how far are the data points from the average of the data points. So how much spread is there in the data generally, and then that's what this is. And then this is measuring how much spread is there away from after putting in the model. So you can see here, for instance, there's a lot of spread in the y's. The y's can be very high, the y's can be very low. So there's going to be a big SST is big. Okay, but the SSR, how far are the points from the data, is small. The SSR is small. Okay, is small. So let's do this other example too. So here you can also see the same exact thing. In the first case, there's lots of small values and big values in there. And so the SST is big, but there's lots of space between the model and the data points. So what does that mean? It means that the SSR is also big. It's big too. Okay. So what we do to measure our R squared, I'm sure you've heard of R squared. R squared is just our measure of fit. So to measure how much, how well a line fits the data, we calculate basically what is the share of the variation in the data that's explained by our model, explained by our variables. And to calculate that, all we do is we take 1 and we subtract the SSR over the SST. So it's what fraction of the total variation is explained by our model. And then we're just subtracting that from 1. So what we get is that the R squared will fall between 0 and 1. And a value close to 1 implies that the regression the data fit very well. The line fits the data very well. R squared close to 0 means that our regression doesn't explain very much of the doesn't explain very much of the variation. Okay, so this will almost certainly be on the exam in some form. I can't remember if I give you the SSR and the SST and you just have to calculate it, or I give you some data and some predicted values. I can't remember, but is a really important feature of econometrics is just what is the R squared and what does that mean? All it means is what fraction of the variation in the data is explained by the model. You can see here, this line is explaining a huge deal of the variation in the data points. Here, this line is not explaining very much about the data. Okay. Questions on those, on that? Okay, so here's a little example. We have, we've got some data. We've got our X and our Y. And I'm going to do a little bit of work for you and just show you that these are the predicted values. And this is obviously the average is the same for each row. The average Y is the same for each row. So the SSR is just the distance between each of the actual Y values and the predicted Y. So the predicted Y is going to vary, is going to be different for each of the observations. So first we have 2 minus 3, that's what this is, 2 minus 3 squared, 6 minus 4, 6 minus 4 squared, 3 minus 5, 3 minus 5 squared, 8 minus 6, 8 minus 6 squared, 6 minus 7, 6 minus 7 squared. And when we do those subtractions and then multiply them each by themselves, we'll get 14. So what does that mean? It means that basically the amount of variance in Y from its predicted value is 14. The SST is just what is the variance in Y from its mean instead of its predicted value. So it's a similar equation, except it's going to be, instead of 3 and 4 and 5 and 6, it's going to be 5 and 5 and 5 and 5. So 2 minus 5, 6 minus 5, 3 minus 5, 8 minus 5, etc. And when we do all that, we're going to find that the sum of squared totals is going to be 24. And then to calculate the R squared, all we'll do is follow this little formula that we've had before, 1 minus SSR over SST. And so that's going to be here, the SSR over SST. And we'll find that the R squared is 0.41. So actually 0.41 is a pretty large R squared. If we ever had that in real life, we'd be like, that's a lot of the variation that we're explaining. Yeah, just a lot. Okay, questions on that? Questions here. Daniel, Devin, Danielson, Cameron, Esmeralda, Ibrahim, Katrina. No questions. You guys, okay. Questions are good, just so you know. Questions are good. They help. I often am saying things that can be confusing. So sometimes questions can be helpful, but maybe you guys are just on top. Okay. So we're not going to do this data bit. I guess I'll just, if there is, it's really simple. Just, I'm not even planning on quizzing you or testing you on it, but if you go into data and you're in data and you just type in regress YX, you will get, it will do all this work for you and produce a table that looks like this. And this table is probably a big mess if you're not used to it, but it's fun because it shows you what's the number of observations. Oh, bother. Number of observations is 5. The R squared, it gives us is 0.416. That's what we calculated by ourselves. Look at this, the SSR is 14, just like we already calculated. The SST is 24. And then here we haven't, oh, we do have this already. So the coefficient, the constant, the beta naught is 2, and the beta 1 is 1. So that's, we've actually used this data before. Okay. And that is that. So if I don't think you need to know regression output or regression commands on the test, but I will check on that, and I'll either take those out or I'll tell you exactly what's on the test in terms of the command. Okay. Yeah, it is actually just like the pace of this semester is really fast. So we've gone through almost half of a class in 2 weeks, which is just amazing. Okay, so let's take a break. I kind of want to show you this outside before they're all gone. Let me put my shoes on really quick. We just got home from Idaho. My wife is from. We're visiting Papa and Grams. And when we got back, the crepe myrtles were just like exploding. This is so fun. It's like the trees are like more red and pink than they are green, which is just super cool. And then this one's doing pretty well. That one over there is kind of losing its flowers. And then the cool thing is, like, I don't know if you can tell, but it's a carpet of flowers on the floor. They're just everywhere. The soil looks pink instead of brown. So these are fun. Okay. Okay, let me give you a little quote I read that I thought was pretty interesting. So this is a guy who, his father was an ardent British communist. And so he was raised reading communist propaganda growing up. There was a book that Stalin wrote called A Short History. And ironically, it wasn't short. It was very, very long and very dense. And so as an adult, he went to every communist country in the world and he studied them. And he's just a very interesting writer. He said, in my study of communist societies, I came to the conclusion that the purpose of communist propaganda was not to persuade or convince, nor to inform, but to humiliate. And therefore, the less it corresponded to reality, the better. When people are forced to remain silent, when they are being told the most obvious lies, or even worse, when they are forced to repeat the lies themselves, they lose once all of their sense of probity. What is probity? That's a good question. Probity is like their sense of honesty and decency. So they're kind of being made to lie. They lose their sense of their honesty. To agree to obvious lies is to cooperate with evil and in small ways become evil oneself. One standing to resist anything is therefore eroded and even destroyed. A society of emasculated liars is easy to control. And then he says, I think if you examine political correctness, it has the same effect and is intended to. But I thought that was very interesting. There's been just sort of an avalanche of lies from political leaders and from the media in particular. And then they'll come out and they'll say, yeah, that was a lie, and that was a lie, that was a lie. And you're just like, wow. Why? Anyway, it's just a very interesting time we live in, a time of chaos and madness. Let's see here. Lost my. It's called a crepe myrtle. They're awesome, crepe myrtle. And their bark is gorgeous, and their branching is really pretty. And so at night, we just moved here actually, and the former owners, they put lights that cast up the trunks at night. And we didn't know that when we bought the place, but at night they're just really, really pretty. The bark is really pretty.
Yeah, it was really pretty, but we were like, oh my gosh, why is the tree red?
Right? I know, it looks like it should be like in a Pixar movie or like some sort of like Avatar show or something like that. Like yeah, it's a really amazing tree. Trees are so amazing. I just like, I have a bit of a tree problem. My wife, I'm always like looking at trees, and my wife's like, honey, it's just a tree. I'm like, yeah, but it's pretty cool. Let me see. Why don't I have lesson 5? What? Nope. Okay, I need to download one thing. I thought I had this here. Let me see. Lesson 5, 4. It's so frustrating. I will have something right here, and then yeah, the tree that I'm really like excited about right now is called a live oak. And it's a very strange tree because it's evergreen. So most trees that look like, they have branches that go out, and they're not a conifer, they're not evergreen. They lose their leaves. But it's this really pretty evergreen tree. Let me download this. Oh, maybe this is why. Lesson 5. Nope. Okay. Let me download this really quick. Hopefully it's really quick. Questions, you guys? Okay.
Are the live oak trees the ones with like the really long branches?
They have really, yeah, they have really long branches, so they can extend out up to 100 feet. They can be 100 feet across and 80 feet tall. So they're great climbing trees. They're great kind of like, they're the trees you kind of like think of when you think of like a big tree. Let's see. they grow here. That's the other thing. They need water, so that's like you kind of want to always think about getting something drought resistant in case we have a water shortage, but they grow here pretty well. Do you like trees? Sounds like I have a tree friend. Let's see.
Have you ever gone to see what is it called? Sorry, my neighbors. The General Sherman tree, I think, the tallest tree or the largest.
No, is it cool?
Yeah, I went to go see it at the Sequoia National Park like a few years ago, and it was pretty cool.
I know, I need to go there. I need to go. That would be really cool. Okay, this is just 1 sec. Yeah, I do need to go there. Let me write this. Okay, well, I can show it to you, but I don't think I can write on this, which is a big problem. Mhm. Okay, there we go. Okay, let me share my screen. Okay. So, okay, so we have these cool regressions. Regressions are fun. One of just the important parts about understanding our regressions is understanding the units that our data are measured in. So it's kind of a key feature of interpreting our regressions is what are the units and how does a regression change as if the units change. Okay. So how do we interpret a regression of coefficients if the y or the x are not just continuous variables, but if they could be binary, or they could be natural logs, or they could be counts. They could be all sorts of things that are not totally what we've been looking at so far. So the two big ones are when y or x are what we call dummy variables, and that's just another word for binary or Boolean. We sometimes call them dummy. It's just 1 or 0. That sounds kind of disparaging, but and then sometimes we take our x or y and we use the natural logarithm of x or y rather than the raw data, and I'll show you reasons for that in a minute. I mean, actually, we probably won't get through it today, but we'll work on it, work towards it. Okay, so what we'll probably get through today are variable scaling with explanatory variables. Remember, the explanatory variables are our x's, and scaling of our outcome variables, and our outcome variables are our y's, our left-hand side. So these are right-hand side, left-hand side. Okay, and then we'll work towards a couple other things. We'll see how far we get today. Okay, so we've seen this. This was what we were just working on in our last slide deck. So suppose that we wish to know how CEO salary responds to the profits that a company's earning. So we can calculate a regression with salary in terms of dollars and profits in terms of dollars and get the following result. So this is actually a slightly different, the numbers are slightly different, I'm so sorry, in this example. So we have CEO salary, in terms of profits, and here the profits is in terms of dollars. So that might not make sense, but we could measure profits either in terms of like million, dollars like this. This is in dollars. Or we might be able to measure it instead in terms of millions of dollars. Millions. Where the unit, instead of putting this into the data set, we might put just 1.0 into the data set. That would be $1 million. So the idea, but for right now, we're just going to use dollars. We're just going to use this part up here. But I just wanted to clarify where we're going, millions of dollars or dollars. So how do we interpret the coefficient on profits? How do we interpret this 0.03? So the way that I would interpret it if someone asked me is I'd say the CEO is predicted to earn something like $400,000 plus 3 cents for every dollar the company earns in profit. And that is another way to think of it is he earns $400 plus 3% of profits. Okay, those are the same. What would the predicted salary be if the company's profits were $10 million? So all we would do is plug in $10 million times 3%. So what I always do when I have something like 3% is say, what's 1% of 10 million? And I just move the decimal place 2. Get rid of these. So I say, okay, so 1% of 10 million is like 100,000, and then 3 times 1% is 300,000. So I get that the predicted salary, if a company's profits were $10 million, would be 400K plus 300K, which is 7. Did anyone do that and get something different? Ooh. Okay. Okay, so what if instead we calculate the regression with salary in terms of dollars and profits in terms of millions of dollars? So now instead of having 1,000,000 in the data set, we're going to have 1 for $1 million. We would get the following result, 400,000 plus 30K times the number of millions of dollars in profit. So how do we interpret the coefficient on profits? All this says is that a CEO is predicted to earn 400K plus 30K for every $1 million that the company earns in profits. And we can do the math that we had before. So say that they had $10 million in profits. We're going to multiply 30K by 10, and we're going to add to it 400,000. And that, just like before, is going to give us 700,000. So the important thing here is no matter what units profits are in, the result of, it doesn't matter, the result that we find for predicting values is going to be the exact same. That's really important. Doesn't matter what the units are in. Great. Those are really pretty. I have seen a jacaranda tree. Are you saying that the Palo Verde jacaranda is your favorite? Is that right? Yeah, the jacarandas are super cool. Yeah, so you're going to get the same value from predicting no matter what units the profits are in. Okay, so that's going to be useful. So let me just give you an example of what the data actually might look like in these examples. So here we could have salary in terms of dollars. Remember, we had salary in terms of dollars in both examples. And we had the profits. I guess we have sales here in terms of dollars in the first example. And then to make them in terms of millions of dollars, we're just going to take those values and divide by 1 million. Okay. We're just dividing by 1 million. So $12 million is the same as, I'm sorry, $21 million is the same as 21 millions of dollars. And so this is just a little example. Show you what the data actually look like. The values are different, but they're just in different units. They're just describing it in different terms. Okay. So this is a really cool thing. So we've talked a little bit about some of the properties of covariance and variance and stuff. So the idea is, question is, what if we multiplied x by a constant, okay? A, for example. So in our example, say we multiplied x by a constant a, which is 1 over 1 million. We're interested in putting the x in terms of millions of dollars rather than in terms of dollars. Okay. So what does that do to the beta 1 and the beta naught that we estimate? So we can actually use our formula for beta 1 and beta naught to understand how changing the x, or in fact changing the y, which we'll do in a little bit, affects the beta parameter that we estimate. So our new x, our new x is going to be the old x times a. So the new beta is going to be, so imagine that we have, this is our original beta, is just the relationship between x and y, and the new beta is going to be the relationship between ax and the y. So two things that we know. One is when we take a constant out of a variance, it becomes squared. And we can take any constant out of a covariance and it will just remain as a constant, okay? So that's all we've done here is we've pulled out the a from the covariance, pulled out the a from the variance, which is a squared when you take it out of the variance. And then we can cancel out the top a with one of the a terms in the denominator. And so what we find is that the new beta is going to be equal to this expression here. Covariance times covariance of x and y over a times the variance of x. And what we notice, this will just make it kind of simple to understand what's going on, is that this is our old beta 1. So we can show what the new beta 1 is in terms of the old beta 1. How do the new and old beta 1 compare? The way that you know that we're talking about a new beta 1 is that we put a little star on the new beta 1. What is beta 1 star compared to beta 1, the original beta 1? And so if we multiplied can you guys see and hear me? my screen changed for some reason. Okay.
Yes, we can.
Okay, sorry about that. That's great. So if we multiplied our x by 1/1,000,000, for instance, what we would find is that the new beta was 1/1,000,000 times the old beta. Or if we multiplied the x by 2, we would find that the new beta is 1/2 of the old beta. Okay. So the second one is much simpler. So when we recalculate the new beta naught, what we'll find is that it actually has that changing an x parameter has no effect on the y-intercept. So we're going to put this, we're going to plug in the old x where the new x was. So it's in terms of the old x, a times x bar. And what are we doing here? We've got I'm missing something. I don't understand. Well, I'm not going to get bogged down, but I'll come back and check this and tell you tomorrow. But the key is that when you add a constant to an x, it doesn't change the y-intercept. And the reason for that is actually really intuitive. So say we had a variable here, and we have a line going like this, and we can multiply the x dimension by a number and make it more spread out, or we can multiply it by an x number that's very small and make it all scrunched up. It doesn't really matter how scrunched up or so say we spread x out. Let me see, if I spread x out, then the slope will be more shallow. So say we're going to spread x out and we're going to make it more shallow. Oh, I'm going to mess up because I can't get it to go through the same point, but oops. So let me think. If you make x more spread out, it makes beta more shallow. So we're going to try to spread it out. I'm going to make, this isn't very straight, but it's going to make the slope more shallow, but it's not going to have any effect on where it crosses the y-axis. Because whenever you put in 0 to the new function, it's not going to change. It doesn't matter whenever you put x times any constant times 0 will still be 0, and therefore the intercept will not be changed when you change the scaling of x. So the only thing I want you to draw from here and really remember is that when we multiply x by an a, the new beta will be related to the old beta in a very specific way. If we multiplied x by a, the new beta will be the old beta divided by a. Okay, and when we do the same thing when we're considering beta naught, the new beta naught is exactly the same as the old beta naught. So that's very, very nice. Okay. Questions on that? Levi, Manuel, Ned, Noah, Steph, Warren, Yesenia. Okay. I'm actually just a little bit lightheaded, so I'm going to call it for today, but we will resume this on Monday. So the key things I don't want you to miss is that your homework is due tonight. The first homework that we did on Tuesday is due tonight. I don't want you to miss those points. Your second homework that we started on Wednesday is due tomorrow. I don't want you to miss those points. And there's a quiz that's already posted, and that I'd like you to take tomorrow, but you can take it anytime through Saturday at midnight. And it's 5 questions that I've said that I've sent you in your email. So that should be those should all be easy points. I don't want you to miss those. And I will try to get you out a review sheet. Some of the things on the review sheet won't be things that we've covered yet. If we don't get them covered and reviewed by the time that the test comes around, you will not have to worry about them. Okay. So when you look at the review sheet, I don't want you to freak out. It will all be okay. I will prune the test to only cover the things that you've seen and that you should reasonably be able to feel comfortable with. Okay. So that's the end of today, and you're welcome to go, and I will hang back and take questions.